ever wondered how train brakes work? It might seem like a simple question, but the answer is a complex blend of engineering, physics, and quite frankly, genius. Allowing a multi-ton behemoth to slow down smoothly and safely is no small feat. The braking system of a train is an integral part of its design, a marvel of modern engineering that ensures our journeys are not only fast and efficient, but also safe. Without effective brakes, trains would be like a runaway roller coaster, a disaster waiting to happen. The brakes are the unsung heroes of the railway, working tirelessly behind the scenes to keep us safe. From the humble beginnings of mechanical brakes to the modern marvels of electromagnetic systems, the evolution of train brakes is a testament to human ingenuity and perseverance. Understanding the mechanics of train brakes is a fascinating journey, so buckle up as we dive into the world of train brakes. To understand train brakes, we first need to grasp the basics of braking. Now, the basic principle of braking is quite simple. It's all about converting one form of energy into another. In this case, we're talking about kinetic energy, the energy of motion. When a train is hurtling down the tracks, it's brimming with kinetic energy. The job of the brakes is to take that kinetic energy and convert it into heat. Now, you might be thinking, heat? Why heat? Here's why. Heat is energy that can be easily dissipated or spread out into the surrounding environment. When the brakes apply friction to the train's wheels, that kinetic energy is transformed into heat, slowing the train down. This heat is then radiated away into the atmosphere, effectively getting rid of the energy that was keeping the train moving. Now, it's important to note that brakes need to be both powerful and controllable. Trains are massive, and they can carry astounding amounts of cargo. That means there's a lot of kinetic energy to deal with. The brakes need to be powerful enough to handle that energy, but they also need to be controllable. After all, we don't want the train to stop suddenly, as that could be dangerous for passengers and cargo alike. So the brakes need to be able to apply just the right amount of friction. Too little, and the train won't stop in time. Too much, and the train could skid or worse, derail. It's a delicate balance, and it's one that brake systems have been fine-tuned to achieve over years of development and refinement. To sum up, the braking system of a train is a marvel of engineering that transforms the kinetic energy of a moving train into heat, effectively slowing it down in a controlled manner. It's a system that needs to be both powerful and controllable to ensure the safe and efficient operation of the train. Now that we've covered the basics of braking, we can delve into the specifics of train brakes. The most common type of braking system in trains is the air brake. Now let's delve into the mechanics of this fascinating system. Air brakes use the power of compressed air, or more accurately, the variance in air pressure, to control the application and release of train brakes. The concept of air brakes is rather ingenious and involves three primary components: the brake pipe, the triple valve, and the brake cylinder. The brake pipe runs the length of the train, carrying high-pressure air. When the pressure in the brake pipe is high, the brakes are released, but when the pressure drops, the brakes are applied. It's a bit counterintuitive, right? But it's designed this way for an excellent reason: safety. If there's a sudden loss of air pressure, say due to a rupture in the brake pipe, the brakes will automatically apply, bringing the train to a safe stop. The triple valve plays a crucial role in controlling the brake application and release. It senses the air pressure in the brake pipe and adjusts the pressure in the brake cylinder accordingly. When the brake pipe pressure drops, the triple valve allows air from the auxiliary reservoir to flow into the brake cylinder, applying the brakes. And when the pressure in the brake pipe increases, the triple valve releases the air from the brake cylinder, releasing the brakes. The brake cylinder is where the real action happens. It's connected to the train's wheels through a series of rods and levers. When air flows into the brake cylinder, it pushes a piston out. This movement is transferred through the rods and levers to apply the brakes on the wheels. This system is not just efficient, but also robust and reliable, making it the preferred choice for most trains. The air brake system is designed to be fail-safe, meaning that any failure in the system will lead to the brakes being applied, ensuring the safety of the passengers and crew. Air brakes, with their reliability and power, are truly the backbone of train braking systems. The man who revolutionized train braking was none other than George Westinghouse. This industrious American entrepreneur, born in the mid-19th century, had a knack for inventions that would transform not just the railway industry but the whole world. George Westinghouse was a prolific inventor. His name is tied to over 300 patents, but the one that stands out most, especially to train enthusiasts, is the railway air brake, patented in 1869. This invention was a significant leap forward in the field of transportation safety. Before Westinghouse, train braking was a hazardous and unreliable affair. Brakemen had to manually apply brakes on each car, running from one to the next along the tops of the moving train. Not only was this process dangerous, but it also meant that brakes weren't applied simultaneously throughout the train, leading to jarring, uneven stops. But Westinghouse, seeing the inherent risks and inefficiency in this system, sought a better solution. He devised a system using air pressure. The genius of this invention lay in its simplicity. When the engineer needed to apply the brakes, he would decrease the pressure in the train's brake pipe. This reduction in pressure would trigger the brakes in each car, applying them all at once. The result? A smooth, controlled stop, drastically reducing the risk of derailments and accidents. This system was not just safer, but also more efficient. It allowed for the operation of longer trains, as the air brake system could be applied uniformly across any number of cars. It was a pivotal development that paved the way for the growth and expansion of the railway industry. But Westinghouse didn't stop there. He continued to improve upon his design, introducing the automatic air brake in the late 80s. This system would apply the brakes automatically if the air pressure in the brake pipe dropped too rapidly, adding an extra layer of safety. Westinghouse's invention was a game changer, making train travel significantly safer. His genius laid the groundwork for today's modern train braking systems, testament to the enduring legacy of his innovative spirit. While air brakes are still widely used, modern train braking systems have seen significant advancements. First, let's talk about dynamic brakes. Dynamic braking is a method used to slow down or control the speed of vehicles. In the case of trains, it's used as a supplementary braking system to the traditional air brakes. But what makes it so special? In simple terms, dynamic braking uses the train's own motors to generate resistance against the forward motion of the train. So instead of applying physical pressure to halt the train, as in the case of air brakes, dynamic braking uses the train's own momentum against itself. It's rather like trying to pedal a bicycle uphill. The harder you pedal, the harder it becomes to move forward. That's dynamic braking in a nutshell. It's a clever system that provides extra control while reducing the wear and tear on the mechanical parts. Now let's move on to regenerative brakes. Regenerative braking is a step up from dynamic braking. It takes the concept of dynamic braking and adds an extra layer of efficiency. Instead of just resisting the train's forward motion, regenerative braking systems convert the train's kinetic energy back into electrical energy. This reclaimed energy can then be fed back into the train's electrical system or even into the power grid. It's a win-win situation. The train slows down, and the energy that would otherwise be wasted is put to good use. This is the brilliance of modern train braking systems. They are not just about halting a massive vehicle on the tracks. They are about doing it in the most efficient and sustainable way possible. By converting kinetic energy back into electrical energy, these systems are making the most out of every joule of energy. Modern train braking systems are a testament to human ingenuity. They represent our constant strive for improvement, for finding better and smarter ways to do things. These modern braking systems not only provide excellent control, but also contribute to energy efficiency. So, there we have it, a journey into the world of train brakes. We've delved into the basics of braking, understanding that it's more than just stopping a train. We've looked at air brakes, the backbone of train braking systems, and how they function to ensure safety and efficiency in our railways. We've also paid homage to the genius of George Westinghouse, whose innovations in train braking systems transformed the railway industry. His invention, the air brake, has been instrumental in revolutionizing train travel, making it safer and more reliable. Finally, we explored modern train braking systems. We've seen how technology has evolved, incorporating elements such as computer systems and magnetic brakes to make train travel even safer and more efficient. So remember, next time you're on a train, appreciate the incredible engineering that goes into stopping that massive machine. Until next time, keep exploring the fascinating world of trains.